Okay, I'm going to get started. This is work done with Helen. She's in my group. She used to work in Palantir before. She works in Instart now. Quite brilliant. She came to me after she finished undergrad. She has a couple of papers out on arXiv, one that's still under review. And also collaboration with Jasvir. He used to be in Google's security team. He wrote Kaha, which you might be familiar with if you're in the JavaScript world. He runs the product security in Instart now. So let me actually tell you a little bit about who am I. There are a couple of people that actually know who I am, but if in case you don't. I run the data science and machine learning group at Instart. I have a couple of slides about what the company does later on. I used to be a lab head in Howard Hughes Medical Institute. It's a privately funded NIH-like setup. I used to do experiments and theoretical work on explaining behavior of the animals using lots and lots of recordings from the model systems. I particularly worked in Drosophila, right? And I used optogenetics and techniques of this kind. Before that, I used to be a postdoc with Gene, who used to be in Berkeley. He's famous for a bunch of stuff he did in Celera. Before that, I was a grad student here. My committee was Shankar, Jitendra, and Sandrine, who is in statistics. We are somewhat of a small company, but not too small. We work in the web application delivery domain. We have pretty good list of venture capitalists that funded our company, doing very well. I would say essentially we are past the existential problem space. We are more in the how to get bigger phase, which means that there's a group like mine, which functions most like skunk works within the company that essentially is much more strategic looking forward. I built at least two of Instart's very important products that are currently in the portfolio. And I used to be an advisor before I joined them full time. We have 150 or so enterprises that we serve. We are very much an enterprise company. So there are B2C, B2B companies. We are a B2B company. Our customers are large enterprises. And some of the customers that I will show later on in my experimental data, they're fairly large. They're large to the size where if you look at their log lines for a day, it will be like a couple of billion log lines a day. Right? They're reasonably large. So there's a classic dichotomy in security. Right? There are two ways people usually think about security problems that at least I have come to understand. One is by security by construction. Right? So the idea is that you build sandbox after sandbox, you build rules about how things should be done, and you try to create access control mechanisms. You try to essentially create a very safe environment so that everything is secure. So the problem with this mindset is that if you build a perfectly safe, secure environment, probably nobody will use it because it's not that useful. Right? So there is a tension in trying to really be secure by construction and being useful. And the other crowd is essentially just says, build whatever, just patrol a lot, try to pick up what's going wrong by looking at lots and lots of data, and use that to drive your security. Obviously, this school of thought also has problems because it's easy to miss things. Sometimes if you miss something that's very important, the cost is extremely high. And even if you can catch problems fast and quick, there is no reason not to be safe, right? So really, even though there are these two schools of thought that really fight against each other in security, they should be working more together. And the talk is about how they sort of interface. So why is it that web application security became very hot at this point? There are a lot of black swan events, right? I mean, you probably heard about what happened with Cloudflare recently, and there are many, many examples where something goes wrong, it brings out 1/3, 1/4 of the internet down, you can't go to Amazon, you can't do anything, everything is blocked. And the internet is such a huge part of everyday life that these kinds of events have massive real-world impact, not just financially, but Maybe you're going to have a date and the website is not working and your day is really crappy. So it's such a central part of everyday life. Like WeChat, for example, if you go to China, you can't get out of the house without using WeChat because everything is in this web application. From that context, I feel like the black swan events and the possibility of fraud makes web application security very hot, topic-wise. The question is, how can machine learning help in this security domain? So you know the picture. You probably know the code that's going to come. I use this code to make sense of dealing with security people. And what I've come to realize is that the code goes, there are known knowns. These are things that we know that we know. There are known unknowns. That is to say, there are things that we know we don't know. So I put them in green because I feel like these green lines represent the security by construction mindset, right? They're talking about having an idea how things should be done and protecting against them. But the reality is that most of the web applications are dynamic. They are composed in on a client. They're dynamic, so you really don't have control over them. And most of the web applications are written in JavaScript, which by no means is secure by any sense of the word. So the reality of life is that there are lots of unknowns when you have a web application that you're trying to use. So it's worth basically focusing on the unknown unknowns. These are the things that we know, we don't know that we don't know. Can we figure out somewhere where that something is off? So the red part is what I'm saying is more of the security by patrol category, and the green parts are more of the security by construction. So I'm going backwards. This is a data flow of somebody that is trying to interact with the web application. So this could be a browser. This is some very thin client from Instart that sits in your browser. I'm using the data flow from our company's website, but it's fairly general. If you go to Google or if you go to Amazon, it will look with small modifications very much the same. There is a user that's trying to interact. There are some third-party things that are sitting in your web application. Everything that's all the access patterns that are happening between the user and the web application are being logged. There is a blacklist that essentially stops things that shouldn't happen, right? And if some violations happen, they get written into a database. And there is some report that gets generated, and it'll go to some customer. Let's say New York Times is your customer, Washington Post is your customer. It goes to the customer saying, hey, this kind of thing happened, and they get a report. This is usually the data flow. The reality is that there is a giant space here where lots and lots of data goes and nothing happens. So it's what I call the dark matter of security. And this has been observed before by other people. It's not me saying first. So there is this slide from Josh Sachs from Invincia Labs saying there are terabytes of logs generated every day by the enterprise that nobody examines ever. And there is a lot of user behavior data that could be potentially interesting, but no one really makes use of it either. So this reminds me of a story. When I was a grad student here, I used to work on this project called Camera Sensor Networks. We talked to lots of different universities, companies, San Francisco Police Department, and so on. There is an anecdote where we found out that University of Washington, Washington University, which is in the DC area, they were essentially contracted by the federal government to store all the feeds of the cameras that were monitoring the DC, right? I think it was George Mason University that was storing all the feeds. Now they got paid $1 million every month to store the feeds, right? So the joke was that nobody ever looked at them, right? The feeds come, they get into the database, they get flushed out 3 months later, but nobody did anything. And that observation was the root of some work we did in video activity recognition. But in security today in enterprise, this situation is not that far off. There are companies like Splunk that are trying to organize the data better, but there is a lot of space in how to use that data in some systematic way to make sense. Now, when I first started talking to the security people in my company, they really disliked the idea of using machine learning, right? Because they have been burned by this before. So I'm going to actually talk about how you will feel if you go into a room full of security people. So we ran a workshop with Dan Bonnet last year in Stanford. If you don't know Dan Bonnet, he's probably the #1 cited researcher in security field. And there's a room full of security people. The entire, almost 2/3 of the day went into how machine learning sucks. And I am the speaker right after, so it was really fun. But some of the feedback that you get when you start talking to the security people about machine learning is that it's just a marketing buzzword, or it's just stats. You basically put a little bit of a spin on top of it. Or there are also people that essentially, I won't say the company, said, this is going to solve all my problems. I can't wait for it. Right? So the question is it all or none of the above? But generally, if you talk to a sales engineer who works in security and you say machine learning, they don't want to hear it. Okay? Now, where is the reality? The reality is that, so I just want to make sure that I remind you of some things, even though there are a bunch of people here who know about machine learning. See, the term originates from Stanford Bell Labs. It's just instead of coding a function directly, it's programs that essentially try to learn the function relationships by looking at data. That's the inversion, right? A machine learning program doesn't have specification of what it should do. It's supposed to learn that. And this is a cutout that a bunch of you may have seen. This is from New York Times, 1958. What I'm trying to say is that there has always been marketing hype about machine learning. This was before the first AI winter, for those of you who know what that means. Apparently, ML systems were always very expensive. It was $2 million. Some of the things that were said in this article in 1958 have come to be true, right? At this point, if you show an image, the image can be translated to some text. If you show essentially a menu that's in a foreign language and you put your cell phone on top of it, it could probably translate it to you in a language that you can understand. These are things that are sort of spectacular. These things are true, but a whole bunch of things that were written in the same article are not true. We still don't see self-replicating machine learning agents that are somehow intelligent. We also don't see anybody that's shooting themselves to Mars as space explorers because they're smart, right? So the other reminder is that there's a lot of hype about certain types of machine learning techniques. But it's worth remembering that the space is very large. There are lots of different ways of doing machine learning. And when you go to the security as a problem, you should keep all of the picture in mind instead of getting fixated on one particular way of thinking about it. And this is a paper from Wolpert, who used to be a postdoc with Michael Jordan a long time ago. This is called the NFL no free lunch theorem. Basically, what it's saying is that no learning algorithm is inherently superior over other learning algorithms for all problems, which means there is no universal learner that will do great on everything. Just there are 2 papers of this kind. You can look them up. It's an interesting idea to remember because you could have a spectacular hammer, but just make sure that it's a good hammer for the problem. Now, machine learning for security has a really long and rich track record. Even though if you went to RSA in 2015, probably a couple of vendors would talk about using machine learning in security, but machine learning has been used in security for a very long time. So we did a survey about the last 10 years. There was a survey before that, and we put it on archive. So you can go read it. I'm not going to go through all the details, but I will highlight some things that I think are interesting. We didn't cover anything about privacy, evasion tactics, censorship, offense, etc., but we talked a lot about defensive techniques and use of machine learning in defensive techniques. First paper about using machine learning in security came in '87, right? Dorothy Denning still works in Monterey in the Naval Postgraduate School. She worked on using machine learning for doing intrusion detection, and she then later applied these ideas in HP. After that, there was 98-99 where the famous KDD Cup IDS challenge dataset came out. This is a very famous dataset in this domain. It's equivalent to the MNIST data if you're a computer vision guy. After that, in around 2008, 2007, KDD and a couple of other venues started to pay more attention to machine learning and security. There's a famous paper in 2011 from Berkeley, from Doug Tygar's group, about adversarial machine learning. Bunch of other surveys and manifestos have come out. Now, the first cybersecurity grand challenge started last year, right? So if you basically notice the craze around self-driving cars today, you should also remember that a lot of the origins were back in the day when DARPA did the grand challenge, so they're usually offset by several years. So if this is true today, maybe by the time in a few, 7 to 8 years, maybe these problems would be hotter in an industrial sense. In the survey, we covered lots of different use cases. I'll skip that for the sake of time. What we found is that there is a general system design that seems to be true across all these 600 papers or so. So I'm going to talk you through it. What you found is that these dark lines that you see are pretty much true for all the papers that you see in this domain across hundreds of papers. Very common to have a knowledge base from which you train your machine learning model. There are data sources that you use to pre-process, extract feature vector. Very classic stuff, right, if you're a machine learning person. Now, knowledge base, just to define terms, is just the baseline of known normality and abnormality. So in the security sense, it would look like whitelist, blacklist. It's a prior. It's some kind of encoding of your prior. And the data sources are all the data that your machine learning system gets to work with. There could be offline data. There could be online data like a URL stream, behavior data. It could be server-sided or client-sided, depending on what your application is capable of collecting. Training data is the data which has labels. So in computer vision and some of the other fields, at this point, this is very common to see. This is actually one of the things that's very unique to security is that there is no good benchmark. There are some benchmarks that everybody complains about because they have problems. But it's very hard to benchmark things in security because if you have a benchmark and you captured something, the adversary is just going to skip and try to find ways that are not covered in your benchmark, right? So there is a basic adversarial nature to the security as a problem which makes benchmarking hard. Although I do think that there is some need to at least create some benchmarks for just validating that you can do the basic stuff. You know this. I'm not going to go here. So coming back, what I want to highlight is that essentially the feedback about how you use the feedback from the human security expert to improve your system, and how do you handle the interface between machine learning model and the security expert, the human, are the things that seem to be underexplored, right? In a lot of the papers, these are the aspects where there's very little time spent. Actually, in the enterprise sense, this is where most of the things really go to hell, right? If these things don't work, nobody is going to ever care about your product. But these are also the things where you see very little work in the field. So I just want to double-click that to make sure that if you're thinking about this problem as something to work on, these are probably places you want to focus. Now, this is a table, right, that we made. Each row is different type of security. So here by attacker type, here by means of attack, purpose of attack. And the columns are different machine learning methods, right? We did that to essentially highlight that almost 70–80% of the work, majority of the work is in the supervised paradigm. But nobody has these supervised labels, right? So there is a complete disconnect between stuff that gets published and stuff that I can use in my day-to-day life. And this is something we have been talking to a lot of the academics to try to fix. We have run a workshop with Dan last year. We are trying to run another one this year. We think that people need to think about these other columns because they're a lot closer to reality than this first column. A lot of the work essentially assumes that you can make up some data and show something, but it's really a bad assumption to make. But this is the dominant paradigm that's used in the papers. And if you notice, essentially the passive attacker type is actually the most sampled in the rows. But this is also the one that you don't care that much about, or you can actually fix a lot quicker, right? Because you can create a signature. Once you create a signature, because they're passive, you catch them, they're done. These are not the guys that mostly we stay up at night worrying about, but this is the one that gets covered a lot in the papers. So attacks on integrity are also very commonly covered in the purposes of attacks. But if you notice, a lot of the news is more about availability and confidentiality, right? If you attack this and a whole bunch of internet goes down, this is a lot problematic. And this is more about leaking your passwords and stuff. So for example, Yahoo lost $1.5 billion for messing up that part in their sales. Yes, sir?
Can you clarify what you mean by passive versus the other?
Yeah, I have a slide.
Oh.
Good question. So now the question is, when you're designing your machine learning system, I always make sure we talk about this in our group, is that you should assume that everything you know, the attacker is going to find out. How? I don't know. They're going to come have a lunch with your friend somehow. I mean, there is incentive, honestly, to do these things. You know, Kevin Mitnick is famous for breaking into things not because he's a coding wizard, he's because he's social engineering. And that's the easiest way to break a lot of enterprise security. So you should assume that they're going to know everything you know. Can you build a system that can still be robust? So food for thought. What does the attacker know? You should basically think about, they may know your learning algorithm itself. They may know the feature space that you're using. They might know the algorithmic parameter. So if you read basically the paper that came out of Doug Tiger's group, you can see that some of these things can be easily messed up if this knowledge is available to me, because I can attack it. I'll show a couple of examples from real world right now. So a lot of these things, right, you should basically think about, hey, if they know, how do I basically model my system so that I can be safe against it? And if you haven't thought about it, this is something you should think about. This is a slide that I picked off from John Lansbury's talk that came out from DARPA a couple of months ago. Right, this is an example where some deep learning system that was trained to recognize animals, it correctly classifies this as panda. They added some very minute targeted noise to the image. The right-hand picture looks still very much like a panda to you, but the label completely switches over. There's a paper from EPFL that came out last month that's essentially describing how to universally attack any deep learning system. I'm not trying to diss deep learning. I'm just saying that anything that assumes stationarity in your batch process and assumes that you can collect data and freeze it and learn something, you can go after it. And in the security, there is incentive to do so, right? Because there is a lot of money behind that. This is another example where somebody essentially put up, an AI agent, which people basically poisoned by training it in a wrong way, where this tweet bot quickly became a Nazi because people were essentially feeding it very bad training data. Very real-world example of how this can be messed around. What this basically means is that if I know how your AI agent is basically going to be trained or how it operates, what's the parameter space, it's very easy to make them do wrong things. And if basically you're using a machine learning system to do enterprise security, this is a very clear, obvious problem. So this is a question that was asked earlier. Passive means it doesn't do any attempts to evade detection. Threat models capture the behavior of the attacker well. Semi-aggressive means that it has knowledge of the detector, only attempts to avoid detectors. Active means it both has the knowledge and is actively trying to get around. Most of the problems that so these tend to be bots, right? You script something, you just DDoS, send everywhere. These are the very good ones, where they really get under, and they also tend to stay quiet for a long time unless it's time. So coming back, that's the coverage from the table. All this data is in the survey. You don't have to write anything down. I'm just going through. So if you look at machine learning in security today in the enterprise space, that's an example for the no CAPTCHA that came out of Google. I like this result a lot because CAPTCHA was considered very problematic because there was a lot of friction on the user side. There were a lot of people with bad vision, or they were on a wrong kind of a phone that couldn't really break the CAPTCHA, and it was causing UX problems. So this was considered an important breakthrough where Google figured out that they could tell whether it's a robot or not by doing something simple instead of having them solve the CAPTCHA, and this is called no CAPTCHA. In our own work, we have essentially tried to look at how do we go after the enterprise security. So there is a paper on arXiv that it's also under review. We built what's basically like a Netflix for security. So you dump all your enterprise logs into the system, and you go get your coffee, and after 5-10 minutes, it can actually start telling you interpretable recommendations about what's funny in your logs. Right? The key design criteria that we wanted to make sure was that it can actually explain the recommendations that it's making. So our practical lesson in this flow was that when we were talking to the security engineers, if we just told them, this log line is wrong, no one trusts you at all. Right? It's not good enough to have some kind of an accuracy high. You need to actually be able to explain when you're right, when you're wrong, both times. You need to be able to explain why you're saying that. And having the ability to make that explanation actually creates this like confidence in what you're saying. And that turned out to be key in our workflow. This is a block diagram from the Helios paper that's on arXiv. Basically, there's a WAF, the web application firewall, that sits at the top. So whenever anybody is interacting with the web applications that we serve, there's a rule set that gets applied, and all the logs that get through go through some non-parametric pipeline that's in the back. This is also in the paper, so let me skip and get to what's interesting about it. So we can see, at this point, this was an old slide. At this point, we can even see billion log lines every hour. Right? So the scale is very large. We have 150 customers or so. We get traffic from 200 countries or so. You can see any day about 300 to 400 browsers. HTTP methods are supposed to be only mainly 4, but you see all kinds of HTTP methods, arbitrary ones. And there are lots and lots of different MIME types. So if you are essentially trying to make a recommendation to the security user saying, hey, that country, this browser, that particular MIME type is bad, the search is combinatorially large. Right? It's very, very large space to look through. And the system that we built essentially works off of a 2 to 4 core laptop. And it uses Spark, which is necessary in our paradigm. And it can work in pretty much close to real time. So one of the other things that's problematic is that these kinds of recommender systems that we build classically have the problem that they have to deal with cold start. Right? If I'm dealing with a new security expert that just joined the company, I don't know anything about this person. The person doesn't know anything about the data that we are dealing with. So in companies like Pandora or Netflix, when you have a cold start problem, it's been shown that it's very hard to crack. They use lots of other social information gathering to decide what to show you. Because when you just join Pandora or when you just join Netflix, it's really hard to know what you might like. Right? And if you basically mess up, maybe you cancel your subscription. So we have the same problem, and we basically solve these problems using the rank methodology that we showed. What I wanted to get to is this. So this is one of our worst critiques in the company. An extremely good security engineer that ended up using the system that we built. I'm going to try to increase the sound.
We asked Helios to go over a set of 2 customers' logs. We took a 24-hour period and had Helios analyze the logs and suggest any recommendations and give us a bunch of data out. So we thought it'd be best to take the smallest data set first to analyze, which was to have Helios give us recommendations based upon request methods. So looking at request methods, we found customer A had these request methods, as well as customer B having the request methods listed here. So we were able to talk with customer A a little bit more and found out that on their website, they use post, get, put, and delete. So all other methods are unused to them. So head and prop find could be considered suspicious, even though they're legitimate methods, as well as options and connect. G doesn't sound pretty legitimate, neither does cook and ET, so those stand out right away. Now, even though we didn't get to validate any of the request methods with customer B, you can look at some of them and say, oh yeah, these are not legitimate. Patch could be, but ASDF, track is typically considered something that's suspicious at least. XXX, and of course the all-knowing method underscore other is not legitimate. So it was good that we found this. We said, okay, here's the methods we found. These look suspicious. Great, so we've got a minor win. So we wanted to look down into the details a little further, and within each method, we then had Helios provide its recommendation.
So here is an example where the machine learning system is essentially interfacing with the security expert, but it's not just saying that some log line is bad. It's trying to tell the guy what aspects are bad, right? It's actually providing an explanation and certain parameters about the interaction that are bad, which means that he can essentially use them as query parameters, go back to a database, and really figure out and validate in his own way whether he thinks it's funny or not. This back and forth is actually very important, and this is also where the human sits inside this back and forth, right? And because there is a person that's interfacing with the machine learning system, you have to pay attention to how do you present to them in a way that's intuitive, and how do you do it in such a way that they can go and verify on their own and come back to you and trust your result.
So we did mainly a big bulk of our deeper dive on customer A. And that deep dive went pretty much like this. So first of all, it says, okay, here's the request method that we're analyzing. Out of that request method, these three combinations of content type, user agent type, and country, and then Helios's threshold scoring. So we asked it to get the top 5 out of each of these request methods. So for head, we found this grouping, along with application PDF United Kingdom, and then the other 3 down here. So with these, the nice thing is these can all be used as queries into Presto. So what that lets us do is we can say
Presto is the name for our large log database server. It came out of Facebook. We just modified it and use it internally. Yes, sir.
What does that mean?
It's basically the top 5 recommendations for that method. It has some way of computing a score to rank which recommendations are higher or lower. I think essentially those 5 got the same and they were the top 5. So it's just putting out.
Was the training set so tiny?
There is no training.
Oh.
Yeah, important question. Yes. It's basically completely unsupervised, and it's essentially using underlying rank statistics to decide that something's off.
we have the request type, we have the content type, the user agent, and the country. We can use that as a query in Presto and pull back relevant data. So the nice thing is now not in every instance, but really in the majority of the instances, we found a one-to-one mapping, whereas Helios would identify one recommendation out of Helios, actually track back to a single IP address, which is pretty neat. It was kind of neat to see that it could find a specific request.
So this problem, when I first started to work in security, Dan Bonnet described to me as finding the needle in the haystack, right? There is a lot of stuff that's in the logs, and you have to be very specific in the security domain in order to build a rule that blocks somebody. So it's like you're looking for something really small in piece of detail that you can build your rule around. What we're basically showing is that at least empirically, we have found that we can get to that fairly efficiently. So the input logs are probably like 500 billion logs here, and the amount of time it took to crunch it is probably less than half an hour at that time. This used to be on a 2-core laptop. We've modified and hooked it up to like a server now where it can run in 4 minutes.
Digging down into those details, we can take, of course, our typical grouping here of content type vulnerabilities on the site. So it was really kind of neat to see that, oh, great, we saw that this was a precursor to an attack. Great, so Helios did actually find something malicious. We've got a really good win here because we see it's a precursor.
So this is an example where essentially a certain interaction that Helios flagged as funny was not funny at the outset of it, but because it gave you the parameters about what was off, you could go back and localize it in the middle of what's happening. And what you found is that essentially there was a line of attack where the agent would come and probe the website to see if something is true, and if it is true, it would launch a lot of probing things. And we found this across at least 14, 15 different enterprise customers, and we let it run for 2 months and saw that, this happened like 300 to 400 times. And this was something that was previously not known. The cool thing here that I want to highlight is that this is basically discovered automatically, and then we could close the loop and basically put it back into the web application firewall so that, through the person, essentially we can have it as a closed loop web application security system. Another example that I really like is, so this is an example of creating the WAF rule based on the finding and lots of the attacks that they had seen. One of the examples that I actually really like is the case where it was a false positive. So one of the customers had put a look-ahead search in their website. So every time you're typing, let's say, bar soap for BAR, there would be pings going back to the server, and they would look really funny. And essentially, the system said that, hey, this chain of things that are happening is really odd. But when we went to the customer said, hey, they're just the result of the look-ahead search. But they then could decide whether they want the look-ahead search feature or not, because it's also actually bottlenecking their server by creating lots of queries. This is one of these cases where the system tagged something as security anomaly. It wasn't a security anomaly, but we could go to them with a good explanation, right? So when the loop was complete, they actually trusted that we know what we're doing. Whether we are right or wrong, we could actually tell them what's basically the story behind it. This is a plot where it's log of minutes. Purple is our best security person trying to deal with data from so many number of customers. This is system with 1 core, 2 core, 4 cores, right? What you will see is that system doesn't care, right? It basically can parallelize and run queries on all customers at the same time. But for people, they have to do it serially. They can't hold information about all the customers at the same time, so this is a natural bottleneck. And here is one case where essentially, instead of hiring 100 or 50 more people to solve the problem, as we got more and more customers, we could keep a couple of people who are extremely smart and essentially farm out a lot of the intelligence that essentially generate recommendations for them pretty efficiently. So this is the rule that I showed in the demo that we created. It ran over December and January for 60 days. We found hits for at least 15 different enterprise customers using this process that created a closed loop WAF rule. So the data here, this is billions of logs, right? 200 million, 400 million, 600 million logs. Look at the number of times the attack happens. This is a very particular one. It's a very small number, right? Anywhere between 5 and 10, maybe between 0 and 5. But we can pull them out. The problem with it is that it's a very small number. So in a pure supervised learning sense, it's almost like noise, right? But the impact of not catching it financially is very high. So it has this very inverted kind of a behavior where if you can catch this little guy, you basically save a lot of money, and it's very satisfying. Yes?
And all these attacks already made it through their internal security channels.
Sorry?
All of these attacks that you detected were they also detected by your customers?
No. Yeah. So they basically skipped through. They had their own internal systems, and we had our own because they bought service from us. This is one of these where they couldn't pick up, we picked up. And there are some cases where we have also seen that we pick up, they also pick up, and we cross-validate. In some other cases, basically we pick up, they don't, they just do some investigation and turn back. In the security side, because actually both sides want to solve the problem, so the turnaround is fairly quick. Right? Some other information. We also checked to see if we can generalize, and we found that there is this system called WebRoot that people use quite often. If you're in security in the industry space, you might see. WebRoot basically is a reputation for IP addresses. And we found that there are lots of things that we could find that weren't really in the WebRoot system that we could find out new. Okay, so I'm using customer and customer 2 just to keep the names safe. So in the real world, when you're using machine learning for security, there are certain things that we have run into that I'm just going to serially highlight and briefly talk about them. If you have questions about any of it, stop me and I can go deeper. Scale is something that's very important. People assume, if you grew up in using machine learning in the computer vision side, you assume that you can go to the internet, download lots of images, and so on. In the security world, the scale and availability of the labels is not like that. Right? It's kind of hard. The only good place where I have seen availability of lots of labels is the malware side, where people use something called VirusTotal. It's like a co-op that if you pay $100,000 a year, you are welcome to join. And there are 70 or 80 vendors that provide labels. But the problem is that those labels also have inherently jitter. There is a lot of label noise. So you need to be careful about how to use it. The quality, feature quality, and the label noise are something you need to be very careful about. It's not the case that if you throw anything at it, the systems can work fine. And you need to basically think about how do you interpret the answer, how do you explain the answer to the end user who might be your customer. See, in the businesses where you're talking to a customer, probably the person does not have as much power. But in the enterprise side, the customer is a huge person, right? I mean, it could be MSN, it could be Washington Post. They want to know why, and if you don't tell them, like a lot of money just disappears from the table. So we have basically been designing systems which offer an explanation, not just a prediction, but an associated explanation about why this is the case. We have also found that time to discovery, essentially getting to the answer fast, is something that people really like. So there is a lot of data that we have started to show about how we can accelerate time to discovery. It's not, so if you can basically, for example, let's say your time to discovery is in the microseconds or milliseconds, you could even detect attacks that are basically happening right now, right? So there is value in making the TTD as small as possible. You may have to think about operational efficiency of algorithms. For example, there is a system that I built, not in security, but in web application delivery. Originally, I had written it using belief propagation. Right? Belief propagation has n-cube complexity, has number of samples. Then we put it into production, and after it crossed 1 million photos or so, it just started to completely crash our servers. So we had to rewrite it using k-means++. So see, this sounds funny, but it works actually just fine, right? And it is one of these cases where the underlying probabilistic distribution was sufficiently good and data sampling was good enough that a good initialization for k-means worked just as well. So there are trade-offs that you may have to make if you're trying to build systems that work at internet scale. And choice of ML architectures. So one thing that I find funny is that long time ago, when there was a Boltzmann machine talk here from, I think it was from Jeff Hinton, there was this comment about people hand curating features and building machine learning models, how that is bad. You should let the algorithm learn the features. But now if you look at some of the papers that are coming out, essentially instead of feature engineering, there is architecture engineering that's happening, where essentially you change the architecture of the system. And to me, they seem somehow equivalent. And by this ML architecture choice, I also mean that maybe you don't want it fully supervised. Maybe you may want a person in the loop. Maybe you want a semi-supervised architecture if you have some access to partial labels. These are things that are worth thinking up front. Non-stationarity, where essentially either the data or the behavior of how things can go bad can dynamically change. It's extremely important in security. This is something, so in computer vision, what is an adversary that you face? Pose, right? Pose is an adversary where you solve the face recognition like this, you can't solve it like this, then what do? You take more pictures, okay? You can't do that in security because you don't know what the other person is going to do. So there is this adversarial nature that's very hard to model in security space. So from a machine learning point of view, this is very exciting because the standard stuff, it's hard to work with. So we basically have solved it by trying to think about a human in the loop and how do we interface with them, how do we architecture these things, but there might be better ways to do it, and I'm very open to this. The other thing is that you basically want to build systems that produce reproducible results. Your system should be reproducible. You should basically also provide explanations so that there could be trust in the results. If they constantly change and there is noise that makes things go up and down in security, people don't like that. Okay? There could be, in the example that I showed earlier, right, the panda baboon switching thing. In the security world, if there is a couple of pixels that change, sometimes the entire classification of that security problem could change. Like, New York Times was attacked by a widget of the ad that was not even first-party New York Times property. It's a third-party thing. They got into authentication of the ad widget, and then from there they got into the main web application. So what small mistakes you can make, you have to be careful about, because what looks fine on a global scale may not be. It may allow the entry for someone. And there is cursive dimensionality. If you basically start collecting all kinds of data because you want to get all the context, you can't invert your matrix, so it might be difficult. So areas of improvement that I want to highlight is that we think there needs to be better alignment between industry and academia. So when we ran the workshop with Dan Bonnet last year, I asked people, how many people do you know? So let me ask this question. How many of you know what is a web application firewall or used it? Okay. So this split basically tells you how many people have exposure to industry systems and how many people don't. The ones don't, they're in academia. The ones do, they probably spend some time somewhere in the industrial space, right? And there are weird people like me who probably cut both ways, but very few. What I'm trying to use that to say is that there needs to be better crosstalk, because I think we benefit if people in the academia are doing systematic work to actually build systems that we can go and put into production. And you may also benefit from getting data that's much more close to real life by talking to people like us. There's a workshop that happened last year. There's a workshop that we ran in Stanford last year. We are trying to do more of this. Areas of improvement number 2, I think there needs to be better benchmarks. Not simply that it's hard to make benchmarks in security, but there should be some basic things that you should test so that you know that these things work fine. Maybe the exact problem that you're trying to solve is harder. These 2 papers are very famous. They're about the 1998-1999 IDS dataset that was in the field. People know that it has flaws, but it's still one of the best sets. The ImageNet MNIST equivalent of benchmarks, those are computer vision benchmarks, for security don't exist. And recently, DARPA's Cyber Grand Challenge came out. Instead of focusing on benchmarks, they're actually trying to standardize evaluation methodology. I mean, that may also be another way things get standardized. So this is a very hot happening space. And the other thing that I noticed in Strata is that big data used to be very hot and sexy, right? But a lot of that infrastructure now is considered pretty much commonplace. I mean, you can basically get a big data infrastructure put in place in under a week if you hire somebody that's smart. So once that is stable and is available freely, things that you can build on top, like security, for example, or essentially any kind of personalization, these kinds of value-added services on top of big data become very interesting. So the Rise Labs secure execution, privacy kind of stuff that you build on top, I think become very interesting. So these things that usually used to be purely in the machine learning data science domain that now intersects with big data are starting to be very hot. So I mean, for example, I feel that Strata will continue to have these sessions for the next couple of years at least. So where do we think things are going? We still don't see very much of metric learning kind of work in security, and I think there is space for it. There is a lot of space to use natural language processing, because essentially the interface between humans and these web applications is some sort of a language. I haven't seen that many papers that use NLP in a nice way in security space. I think machine learning in security is moving much further upstream. As you saw, Helios essentially is almost the beginning of our chain. Right? Instead of going all the way making some decisions, they are now really part of the flow up much more upstream. How to scale these systems much better is something that I think is going to be very important, because real-time security is extremely incentivized. I mean, a lot of financial institutions will pay you a ton of money if you know how to do that. Specialized probabilistic models. So what do I mean by this? LDA paper, which came out of David Blay and Jordan here, was phenomenal because it proposed, latent Dirichlet allocations for how to model text as topic models, right? Because, I was a grad student here when that happened. For security, there may also be a space to explore probabilistic models that work very well, but I haven't seen anything. So the focus on false positive reduction and fast time to discovery is something that I think will become much more important. And privacy enforcement, like when you're doing a lot of these computations, how do you not leak information so that your information can be private? This particular aspect is almost the #1 driver for health, like medical health kind of applications. And there, that aspect of security is very hot. Lots of things are happening in this space. There is a call for proposals that came out from DARPA last year. We ourselves are working on various kinds of systems. One of them, I showed it to you today. There is some stuff from the survey. I think it's a very interesting area to work in. It's also an area that challenges standard machine learning practices because it has some things that are unique. So it's kind of fun to work on. So my summary is that this is almost the #1 funded area in the venture capital domain to do machine learning in security. But there is a lot of junk there. So if you are the not junk, you might succeed very well. The security itself has some things that are unique that challenge standard machine learning practices, which makes it a very interesting machine learning problem to work on. For example, non-stationarity, adversarial presence, scale, etc. Machine learning presents a really good promise for security needs because it's a way to handle unknown unknowns that standard security practices don't handle. And how to interface these unknown unknowns with the proof by construction type of methods that standard in security is also, I think, important. We are working on essentially forming partnerships between industry and academia. I think it's something that will continue to go on. That's it. I can take questions, but I think I'm just about out of my time. That's to solve the dichotomy, I don't think it's a dichotomy. I think actually it's a circle. And when the problem comes in, it's probably going to either fall on one of these sides, but the flow is always going back and forth. Thank you. Anything that didn't make sense? Yep.
I don't answer that question, but different topics. What about security of cyber physical systems? Can you say something about what we've seen?
We didn't look into it because it's not something that we interface with, but a bunch of the stuff that I pointed out probably port to cyber physical systems. I was Shankar's student. I know Shankar works on this domain quite a lot. In some way, I think the composability issues and the fact that there is security by construction and security by patrol, these issues are there in cyber physical systems too. So for example, reachability type of ideas are more security by construct, right? You're trying to provide guarantees, but they don't work because things could be very dynamic. They could be composed of many weird things. So they work in certain contexts. How do you make them work in a larger, real world context is something you could probably port from here. I don't know of any survey of similar kind in CPS, but Alvaro, Bruno, a bunch of the Shankar's crowd work in this domain. So yeah, I think it's going on. We haven't spent time because my company is very much into the web application delivery. This is something that intersects with us. But And the principal level, I think the problems that we are dealing with like map to cyber physical system domain. I think the data scale is much smaller. That's the one comment I can make. Yeah. And in the Honeywell case, where they're doing these things for IoT, the scale is large, but the computes are very different because the systems are very impoverished. Yes?
Question you brought up in earlier slides, where you mentioned is machine learning just fancy statistics?
Sure. You know, we were not allowed to call it machine learning when I was a grad student here. It was statistical learning.
So to answer your own question, what would you say to that question?
Look, everything in the limit case is some form of stats and math. But it is more than just doing mean median. And for example, the distributions that are underlying like text fields that you see. So for example, if you look at the methods of access and you look at the distributions on these things, they don't behave like standard statistical distributions, right? So I mean, if it's done well and it's done properly, at some point it might become a part of the statistical literature, but there might be some space where it could lead to some interesting new stats. Yeah, we are basically, the Helios recommender system that I showed you, you could basically come to recommendations in two simple ways. One is you do some kind of collaborative filtering that, you know, Netflix, Pandora, they all use, or you could do clustering. But in order to do both of these things, the data needs to have some kind of a real valued property. A lot of our logs are not real valued. It's actually, for me, theoretically, that's one thing that I found really interesting that made us go there. So we solved the problem by using rank statistics. Right? So it's not, it's basically non-parametric statistics. I don't know if that answers your question, but I think there are opportunities where you can actually go do stats, better stats. Yeah. But industrially, it's a very, very hot space, and there is a lot of money in this space. And there is also a lot of space to mess up. I mean, they come together. So, right. Thank you. Thanks a lot.